Now that we have an understanding of path integrals of path-independent vector fields using the fundamental theorem of line integration, we want to next turn to the integral quantity that is going to consume us for the rest of our class today, and that is circulation. Circulation being defined as the line integral of a vector field along a closed curve. So it starts and it ends in the same spot. So we make a complete circuit around whatever shape our path might happen to be. And so the first activity that I'm just going to sort of do for the sake of time, we'll sort of talk through this together, is a way for us to relate the idea of circulation with the idea of path independence. So the question that we sort of begin with on this piece of the activity is what happens, what can we say about a vector field? What can we say about its circulation, its integrals around closed paths, if we know that that vector field is a path-independent vector field? So suppose that I have a path-independent vector field and I've selected 2 points, P and Q, inside of the xy plane. And so I take 2 paths, let's call them C1 and C2, where they both have the same starting point and the same ending point. So they both take us from P to Q. So if this vector field is path independent, then we expect both of the path integrals C1, along C1 and C2 to be the same. They should have the same value. So these 2 path integrals should be equal. So what then should this tell us about the circulation of such a vector field? Well, in order to talk about circulation, we need to discover a closed path in this system somewhere. And I can get a closed path by taking these 2 different paths from P to Q and sort of running one of them in the forward direction to get me from P to Q, and then running the other one in the opposite direction to get me from Q back to P. If I do those 2 things consecutively and stitch them together, then I'm going to get a closed path. Run along C1 and then run oppositely along C2. And so that's what I'm going to do. I'm going to define a closed path C as the concatenation of C1 with the opposite of C2. Right? That's going to start at P and it's going to end at P. So the question is, what can we say about the circulation around that closed path? In other words, the path integral along C, which because it's a loop here, we call it a loop integral, put a little circle on top of the integral sign. What can we say about that value? Well, how could I compute the value of the path integral along C1 followed by the opposite of C2? By the additivity of line integrals, that's the same as the difference. The integral along C1 minus the integral along C2. But what is that difference going to equal, given what we know about the path independence of this vector field? Because we said that they were the same, because of path independence, this first integral and this second integral are the integrals from P to Q along 2 different paths, but those are equal to one another because of path independence. So when I subtract them, the difference is equal to 0. And so what this convinces us is that if we start with a path-independent vector field and we look at the circulation along a closed curve of that vector field, that circulation is always going to be 0. Path-independent vector fields always have 0 circulation around any closed path that we could try to draw. So then what about the opposite? What about the converse of this statement? So there are some vector fields where we might not know off the bat about their path independence, but we might know that all of their loop integrals are equal to 0. And so if I have a vector field that has 0 circulation along every possible closed path, those vector fields get a different name. We call them conservative vector fields. So a conservative vector field is one where no matter what closed path that I draw, the loop integral of my vector field along that closed path is going to be equal to 0. And so then the question would be, can we say anything about the path independence of such a vector field? Well, if we know that the loop integral along any closed path is equal to 0, then I can just pick 2 points that are on my loop, let's call them P and Q, and then use my loop to define 2 different paths from P to Q. One path is going to go from P to Q and it's going to follow my original loop. That's the path I'm going to call C1. And the other path, well, in the beginning it goes from Q back to P along the rest of my original loop C. But if I want 2 different paths from P to Q, I should reverse this second path so that it goes from P to Q instead of from Q to P. So instead of thinking about C2, I want to think about the opposite of C2. So instead of adding the integral along C1 plus the integral along C2 to give me the loop integral around G, I want to think about subtracting the integral along the opposite of C2. So it's like minus a minus is going to give me a plus, right, by the additivity of the integral. But then if we already are convinced that the loop integral is equal to 0, that means this difference is equal to 0, and therefore those two path integrals are equal to one another. And those are both path integrals that take me from P to Q. And so what this convinces us of is that conservative vector fields are path independent as well. That if I have a vector field, all of whose loop integrals are equal to 0, then that guarantees that that vector field is also path independent. We can get from point P to point Q, no matter how we get from P to Q, that path integral, is going to be equal. So we call these conservative vector fields motivated by conservative forces from physics. So in physics, a conservative force is defined as a force which comes from the gradient, usually the opposite of the gradient, of a potential energy surface. So anytime we have a change in potential energy from one place to another place, if I take the minus gradient of that potential energy function, that's going to define for me a force. Right? And the reason it defines a force in a conservative system is that a conservative system is one that wants to move from areas of higher potential energy to areas of lower potential energy. And it wants to do that as quickly as possible. So it wants to follow the opposite of the gradient, which is the direction of greatest decrease of the potential energy function. So they're called conservative because they come from, they're motivated by this idea of gradients, and opposite of gradients of potential energy surfaces in the physics sort of context. And so what this means in particular, let's think about that aviation example that we looked at together during yesterday's class when we were first wrapping our minds around what a line integral is supposed to mean. That we had there a wind velocity field which was constant, right? It was 45 miles per hour due east. And we found out that the integrals there were path independent. Well, they were path independent because that wind field is a gradient field of a scalar potential function, which would be the barometric potential energy function, right? That would tell me that this wind is blowing at a constant rate of 45 miles an hour directly to the east because we have a potential energy function which is sort of sloping downwards with a constant gradient of 45 miles per hour per mile toward the east. And so again, the reason that conservative gets used in this context is motivated by that very common phenomenon from physics, where the reason that we have a force is that we have a gradient of potential energy that we're trying to go downhill on as quickly as possible.